Here we are going to use the last case when the function xs is given as a logarithmic function. So how we can find the inverse Laplace transform from xs? Okay, so if this example is given, suppose xs is equal to log of s plus 3 by s minus 6, then how to find the xt from this angle? So we know that when there is a logarithmic function present in the Laplace transform output, then we have to use the frequency differentiation property of Laplace transform. So we'll see how we can exploit this property for finding the inverse Laplace transform here. Suppose we have taken the first example, xs is equal to log of s plus 3 by s minus 6. So we know that the formula log a by b is equal to log a minus log b. So using that formula we can write this log function as log s plus 3 minus log s minus 6. Okay, so next if we take derivative in the both side, so left side becomes dds of xs. So derivation we are doing with respect to s, so here it becomes log of s, so it becomes 1 by s if you take the derivative. So it is s plus 3 here, so it will be 1 by s plus 3, and here it will be 1 by s minus 6. So we are assuming this fraction 1 by s plus 3 minus 1 by s minus 6 is equal to ys. So we have denoted this by equation 1. So now you see that if we take the inverse Laplace transform from this equation, so inverse Laplace transform we are taking this part only, with this we are keeping aside now. So ys inverse Laplace transform is yt, and the inverse Laplace transform of 1 by s plus 3 minus inverse Laplace transform of 1 by s minus 6 here. So yt equal to this inverse Laplace transform, we can use the property of e to the power minus at ut, so is equal to 1 by s plus a. That property if you use, you can write inverse Laplace transform of 1 by s plus t is equal to 1 by s plus 3. So here a is equal to 3. So if you put e to the power minus at, e to the power minus 3t which will be, so e to the power minus 3t ut minus e to the power minus 6, so it is plus 6t ut. Okay, so you will get this yt. So actually we want to find xt because xs is given, so its inverse is xt, so we want to find xt. So yt is obtained now in equation 2. So how we can find xt? So from equation 1 you can see that ys is equal to dds of xs. So there is a relation between ys and xs, so we can use that relation to find the relation between yt and xt. Since we have obtained yt, so we can get xt using relation between xt and yt, so that we can obtain first from this equation 1. So if you write this ys is equal to dt of xs, so this is a derivation. Suppose ys is equal to derivative of xs, which is Laplace transform of xt, and this is Laplace transform of yt. So this derivative formula we have obtained in properties of Laplace transform, the differentiation in frequency domain. This is the frequency domain output of xt. So if we are doing derivative in frequency domain, it will equivalent to the derivative in time domain. Okay, so no, that is yt is equal to minus txt, because this inverse is yt, but this becomes equal to minus t into xt due to presence of this derivative. Okay, so this property is used here, frequency differentiation property of Laplace transform. So now from 2 and 3, these two equation, you can see the left hand side are equal, then you can equate the right hand side also. So t minus txt is equal to this, so you can write here. So if you write xt here, you divide minus t here, so t, if you keep t here, minus symbol, if you multiply with this, you can make this plus and this minus, So if you make this plus, you can take it in the front, and this minus you can take in the next backside. So it becomes like this: x is equal to e to the power 6t minus e to the power minus 3t by t ut. So this is the process for finding the inverse Laplace transform of logarithmic function, where you need to first expand the logarithm function in a linear form like this using the division formula of logarithm. So after that you have to take derivative of both sides with respect to s, then you will get this type of partial fraction equation. So if you take this function as a third function of y(s), then you can take the inverse Laplace transform of this simply by using the property of shifted unit step signal of this e to the power minus at ut is equal to 1 by s plus a. So that property if you use, you can find the inverse Laplace transform of this and this, and you will get a yt. So since yt we don't need, we actually need xt. So that relation of between ys and x's can be exploited here like this. So if you take this relation of ys and x's, you can take inverse Laplace transform of them to get the relation between yt and xt. So this in time domain becomes like this using the property of Laplace transform frequency differentiation property. Okay, so we have the relation between yt and xt. Since we have already obtained yt, so we can put yt here and we can get the xt value. Okay, like this. So this is the inverse Laplace transform of the given function x is equal to this one. So in this way you can do also for this function also, where you have three functions. You will get another function here, suppose on log s plus log s plus 1 minus log s plus 4. So these three functions will be there, so you can take derivative and you can take inverse Laplace transform, and you can solve this to find the xt. Okay, thank you.